something may be bad, because this is really, really small. This is really small. And at some point it becomes 0 over 0. And then we get not a number. That's what seems to have happened here, because m became not a number before x1. Okay, so that's where the epsilon comes in, right? If x0 minus x1 times x0 minus x1 could use the absolute value instead, but now we're getting basically the square of the difference. If that is smaller than epsilon times epsilon, then we break out of the for loop. We don't continue. We're going to return instead. All right. And we have to give a value of epsilon. Bingo. Okay, but because we're doing it like that, there's no need for a for loop. What we really want is just really depends if we care about potentially working forever. What I think we should do is keep the for loop. So we're going to do a certain amount of steps, say 100 steps, before giving up. Where does the comma come from? Oh. Yeah, so in the worst case, say epsilon is equal to 0. If epsilon is really equal to 0, like the perfect 0, we will never be satisfied unless the function is close enough to being linear that we get lucky, or just things really, because of the finite precision of the computer, it's possible but very unlikely that we will get lucky and we get right exactly to the 0. So you see here we do 100 steps before giving up. We could also say if this is true, or if m is equal to not a number, apparently you need the math library to deal with numbers that are not numbers. Okay, not a number. I see. Oh. Oh, that's... So apparently... apparently when you have a number that is not a number, it's not equal to itself. And it's the only number which has this property. Let's true. Okay, but not so it works, but because of the order, if we write it the way we wrote it before, by the time we see that m is not a number, the damage is done. We know that once we get to not a number, we'll remain there. So that's our little function. How are we doing on time? Maybe we can note that using a trick of the IEEE convention on not a number. So by seeing m before we evaluate this conditional, we can kind of look forward one step. And okay, so we have this function. See that I just mentioned the slope in this reasoning. So one thing that you could do if you had access to the derivative of f, you could add it here, double star, let's df, say, double. And if you add that, you could remove one argument and then just do a smaller iteration. So m is just df of x0, and then you can check you can compute x1 like that by x0 minus f at x0 over m, and then you can see if the difference is small enough and exit if it is. Alright, so there's a way to compress that by using the derivative as a measure of the slope of the function. But you can also do it with 2 points. So instead of, the jargon for that is, if you look at the slope with the derivative, you're looking at the tangent slope, so the line which goes to that point. If you have 2 points on the function and you look at that line which goes to both of these points, it is the secant to the function. One nice thing about this one is that you can combine it pretty easily with the bisection method, because you have 2 points, and the basic idea is that you will